Nathan, Danielle, Samantha, Jonathan. All right. First thing we're going to do is just have a quick practice of our constraints theory so we're not forgetting that. All right. And then, because I was sick on Thursday, I'm going to use a shorter version of the lecture for today, so that we get all the way through it and catch back up on schedule. This version of the lecture does not have the links to the video online that the long version does. So please make sure that you, when you're studying chapter 3, that you look at the video clips in relation to the information in the chapter. All right? So just have a couple of minutes to play with the worksheet, fill this in, think about what examples you could use. Just so that we keep our constraints theory in mind. Goes at the top. Underneath that bit. What goes at the top of the triangle?
Individual descendants.
Individual. Alright, and then you've got to divide individual into its two subgroups. Okay. And think of examples for those. Break.
Got it.
I'm not breaking it. And then what are the what are the two different kinds of constraints that go down on the bottom 2 points? Task and environmental, good. And then see if you can remember what the types of task and environmental would be. Right, so we have two main types of environmental constraints. And we have 3 areas that count as task constraints. Well, this is looking like quite a lot of people have not bought the textbook yet. What's going on with that? Zach, textbook. Why? Right, you have to have the textbook. It is not an option. It is required for the course. I know, I feel like I'm going to break it and push it hard. That's it. So what are the 3 groups for tasks? What are the 3 main types? Task constraint.
Task or environmental?
Tasks.
Just 2 for
2 for environmental.
2 for task. 2 for task group. Should they go on? They supposed to be sweet.
These are good. This is good though. This goes here, and then these 2 are combined. Physical, global kind of. Global isn't a type. It is just global.
These are environmental.
Right. But
So I can just add 3.
yes. Global is a characteristic rather than a type. Right. These 2 are correct. So what goes under task? Global is the characteristic. So it's global. Task constraints are global. Well, they're not. They're specific. Environmental constraints are global. Right? So what are the 3 kinds of task constraints that we said we could manipulate? Equipment, good. That's 1.
Rules guiding task.
Rules, that's good. That's 2.
Goal of the task.
Goal of the task, good. That's 3. Okay? Alright. So make sure that you're starting to get familiar with this model. Right? What does the arrow coming out of the triangle represent? What is the picture of the triangle and the idea of the constraints interacting of interest to us? What is it? What is it driving? What comes from the interaction of these three types of constraints? Behavior, very good. So the kind of movement that I see, the behavior that I see, right, emerges from the interaction of these constraints. So if I change a constraint, then the interaction's different and therefore the movement changes. Right? Okay. All right. Ignore this because I used it for a different class. We're going to look at chapter 3. Very briefly, some biomechanics. Anybody taken biomechanics already? Okay, so for a couple of you, this will be total review of information. All right, and for some of you, this is going to be a very brief introduction to some biomechanical principles that you can't teach movement without understanding. All right? And you can't understand how movement develops without understanding these principles because they impact everything. And then when you take 312, you'll do this in a lot more detail. Okay? All right, so center of gravity. It's a fictional idea. It's abstract. It doesn't really exist. All right? But it's a point that we could say our body revolves around, all right? We act around this point. Actually, you could just pick one segment and say, okay, this segment has a center of mass, all right? But at the moment, we're going to concentrate on just one center of gravity for the whole body. And we have slight sex differences in the position of where you would pinpoint the center of gravity because guys tend to be taller, right? They tend to have broader shoulders and carry more of their weight up high. Girls tend to have wider hips, and so that drops the center of gravity down just a little bit. Right? And when we're looking at trying to locate the center of gravity, it typically is somewhere around here, right? If someone is standing in an anatomical position, center of gravity is going to be somewhere around here, higher or lower, depending upon their height and their body shape. All right? But when we're looking at sports skills, we don't always stay straight. Right? So as we change shape, where the center of gravity is in relation to our body changes. Right? Doesn't have to be actually within the body. So in this instance, in the divo, is in this really, really tight pike position. The center of gravity moves away from here a little bit forward because all his body is folded forwards, right? So it comes forward slightly. In the case of the high jumper here, right? Because they're arching really, really, really hard and all their arms and their legs are on one side, it moves a little bit in that direction. So it would be slightly outside the body of the high jumper when they're arching like that. Okay? Why do we need to know where the center of gravity is? Right? The reason we need to understand where that is that that's where gravity works. Gravity always pulls us down. So if I know where gravity is acting, gives me a picture of why the body is moving in that way. Right? What happens if you throw a ball, what happens if you jump on a spaceship and you go up to the moon and you throw a ball? What happens to the ball?
Slower.
Possibly slower. When you throw the ball, what happens to the ball? Floats. Does it come back? Does it go down? Does it just keep going? Right? So if I throw a ball in the atmosphere where there's no gravity, that ball just keeps going until it hits a star or a planet or a, I don't know, mobile phone thing winging around the world, right? Whatever. It's just going to keep going. When I throw a ball out on the football pitch, what happens to the ball? What shape does the throw look like? Right? So if I throw a ball, does that ball just keep going like it does in space? What happens to it? Okay, so. Right? Is that right? Is that what we see? So, why does this happen, not this happen? Because of gravity. Okay? So, gravity, I've got a force applied to the ball by the person throwing it, but once the ball is in the air, gravity is pulling it down all the time. Okay. The gravitational pull always acts through the center of gravity of a body. Right? So that's relatively easy when I'm looking at a small round ball. It becomes a lot more complicated when I'm looking at a person doing a triple somersault or trying to tackle someone or any other skill you can think of. Alright? So we've got to be aware, we've got to start when we're watching skills, we've got to be able to look at the skill and go, okay, why did that person fall over? Or why didn't they fall over? Do I want them to be on balance? Do I want them to be off balance? Depends on the skill that you're coaching, teaching. Right? Some skills, I need them on balance, and some skills, being on balance, would be a big hindrance. So, to be on balance, my center of gravity, this one point that we're imagining, has to be over my base of support. Alright? Doesn't have to be in the middle of my base of support, it just has to be within. So if you draw an imaginary line around your base, as long as my center of gravity is within that line, I'm on balance. Right? I might be close to losing my balance, but I'm not falling over. Okay. So, if I want someone to be very solid, I don't want anyone to be able to push them over. What do we usually hear coaches tell athletes if we want them not to be able to be pushed over?
Low center of gravity.
Okay. So, feet wide, down low, right? Yes? Okay. If I'm catching a ball or if someone's going to hit me, feet wide, down low, because the wider my feet are, the bigger my base of support is, the harder it is to push me over. Right? Generally, as well, one foot in front of the other, because now I'm harder to push over front back as well as side to side. Right? Bum down as low as you can, because the lower my bum goes, the lower my center of gravity is to the floor, the harder it is to tip me over. Right? Much easier to push that over than it is to push that over. Right? Make sense? Okay? So, how big is the base of support? How high is the center of gravity from the base of support? Base of support doesn't have to be our feet. Right? If I'm a gymnast, it's going to be my hands. Often, if I'm a diver, it's going to be my hands. Okay? And this is really key when we're looking at people who are learning new skills, because if we're asking them to do something on one foot, that is way, way harder than if I ask them to do it on 2 feet. Because now I've only got this tiny base of support to stay on balance. Okay. As soon as I move my center of gravity outside my line of support, I fall off. If I stay in here, it's easy. So it's very, very difficult to stay on balance on one foot, because it's easy to move your center of gravity outside that foot. Okay? If you think about it like almost like a pendulum. Okay? So here's my body. Okay? If we have the girls here, it's going to be a little more wide here. But what's happening here? Okay? If I'm just on one foot, it's easy to tip that over. If I'm on 2 feet, it's more difficult. When we're teaching skills, when we're working with beginners, we always want to make the skill as easy as possible to begin with. So sometimes we might have to adapt things we're teaching to make sure that the base of support is wide, so that they're stable and they can concentrate on the move, not on maintaining their balance. Okay. So, skills with high stability tend to be easier. My base of support has to be quite wide. Skills with low stability, much more difficult, and my base of support is going to be very narrow. So here she's on one hand, and here she's got a nice wide base of support. Right? Think about your own sport, your own skills. How does this apply? So, if I want to see movement, any kind of movement, we're looking at people, but it doesn't matter what you look at, the rules apply the same way, okay? Any kind of movement, the only way something can move is if there's an external force against it. Right? So, if I'm stationary, the only way to move is to apply an external force. It's the only way. So the external force can be linear. That means it acts directly through the center of gravity, and I'm going to move in a linear fashion. Okay. So I can apply the force horizontally, and I move this way. I can apply the force vertically, and I'm going to move this way. If I apply the force outside the center of gravity, we cause rotational movement, angular movement. that's another really interesting one to pay attention to, because sometimes you're looking at someone and you can't work out why they're tipping over when you don't want them to tip over. Right? Where's the force being applied? So, Newton's laws of motion were created a very long time ago. All right? He came up with these ideas, these principles, and so far, with all our cleverness, we've never managed to unprove them or make them go away. They still apply. All right? First law is about inertia. Okay? And inertia is how easy is it to move something. Right? The higher the resistance to movement, the more inertia something has. So an object stays at rest, and an object in motion stays in motion until acted upon by a force. And the amount of force relates to the amount of inertia the object has. Okay? An object at rest stays at rest. So if I am stationary, I remain stationary. An object in motion stays in motion. If I am moving, I stay moving until a force is applied. Okay? So, terminology-wise, momentum is mass times velocity. Inertia is how hard is it to change that momentum. Right? How hard is it to stop something that is moving or move something that is stationary? So if I'm standing still, I have to apply a force in order to move. Okay. But the interesting thing when you look at the force is it's an external force. So me contracting my muscle isn't the thing that moves me. All right, so we'll come back to that in a second. If I'm looking at inertia, how does that apply when I'm teaching a skill? Well, how many of you are baseball players? Okay. How many of you have had elbow injuries? None? No elbow injuries? Elbow injury. Right? So, when you hit the ball, how do you stop the bat? Right? You apply a force. You swing the bat. How did you stop the bat? By another force. Right? And often, that's where the injury comes from. Right? Because you give the bat so much force at the beginning, and it's swinging, it's moving with all this force, and then you have to stop it. And that means you have to apply a force to stop it. Right? So, if you give a big full-size bat to someone who's quite weak, then sometimes what you see happen, or a small person, right, you see this, right? Because the brain can't work out how to stop the thing it got going, and it takes a little bit of time to work out how to apply the force to stop the inertia, to stop the bat. Okay? When we're coaching a sport or in PE, then the goal often of the skill is to get the thing further or faster. So if it's me, if I'm doing a long jump, right? If I'm training long jump, then the goal in long jump is to get me as far away as possible from the takeoff ball. If I'm a quarterback, then the goal is to get the ball as far down the field as quickly as possible. Right? So the goal often is, how do I use Newton's law to get something further and faster? Okay. I have to increase the force that's being applied, and or increase the distance over which the force is applied. Okay? Now, force is very tied up with how strong I am. So in a particular PE class, can I change how strong I am? You come in Monday morning at 10 o'clock and you finish PE at 10:45. Are you stronger at 10:45 than you were at 10 o'clock?
You can be. That's what you do, I guess.
That would be useful, wouldn't it? No, we can't. It takes weeks and weeks and weeks and weeks and weeks and weeks to get stronger. But I can change the distance over which the force is applied, right? So when we watch someone kick a ball, a really, really good athlete takes a huge long step before they kick the ball, right? The other way of increasing distance is by pulling the foot back as far as possible and having as long a time as possible on the swing. Tennis. Big backswing. Shorter the backswing, the less force is applied to the ball. Okay. So, what constraints might stop me doing this? Flexibility. Excellent. Right? So if someone has tight hamstrings or tight groin, soccer players get groin strains all the time because they don't stretch that body part enough for the amount of work they use that. Right? It's everyone does their good hamstring stretches and people forget to do, or they cheat, right? That's the other one. So they do this. Well, that's great, but that's not stretching your hip flexors at all, right? These got to be behind your hip. So if we try to apply the rule and we haven't done the right kind of training, then we can create an injury. Increase in step length would be a linear. I'm able to apply force linearly for longer. Increasing the range of motion allows me to increase the distance rotationally. Remember though, once I've got it going, I have to stop it. So that can be tricky. I've got to be strong enough to stop it. Same with myself, right? When we run, often the injury occurs when we try to stop, not when we start running. Because you have to apply a lot of force to stop the thing that is already moving. Second law. So he has 3, and they're all really useful tools. First one is about inertia. The second one is about acceleration. So an object's force is related to its mass times its acceleration. Okay? So F equals ma. We can flip that around, and that helps us work on understanding acceleration of an object. Acceleration is an object's force divided by the object's mass. So F is an unbalanced force. Mass of the body or the segment or the ball, doesn't really anything, whatever it is you're trying to move. And acceleration is a change in velocity over a change in time. So velocity we often in everyday language use for speed. We say speed and velocity are the same thing. Technically they're not, but that's okay for us. All right? Change in speed, change in velocity over change in time is acceleration. So what if I'm working at a constant velocity, constant speed? I'm on the treadmill and the treadmill is set at 6.5 miles an hour and I'm running on the treadmill at the constant velocity. What's my acceleration? Good. Yeah. Right. 0. Right? If I'm at a constant velocity, acceleration is 0 because acceleration is a change in velocity over a change in time. Right? So if I'm moving at a constant speed, acceleration is always 0. Also useful because in order to change direction in a game, I have to pass through 0. Right? You have to. If I'm on, look at a XY scale. If I'm here and I want to go here, I have to go through 0. Right? So, same thing. If I'm trying to get someone to be really agile and change direction, technically, they have to pass through 0 to do that. That means they've got to apply a force, stop a force, apply another force. So what I'm asking them to do is mechanically very complicated. So law number 3, we've got inertia, we've got acceleration. Law number 3 is action-reaction, and this is often the one that people know instinctively because we use this saying quite a lot. For every action there's an equal and opposite reaction. Action-reaction tends to be the one that we know the idea about. Right? So, what does that mean? That means that every time I push on something, something pushes me back. So in this case, let's go back to our idea about walking. We said that a body that's stationary has to have a force applied in order to start moving. Without a force, it's going to remain stationary. So, think about a footprint in the sand. Okay. If I'm stationary and I start moving, what force made me move? All right, so let's think that through.
But you sinking in the sand.
Okay, good try. Right? Why do we sink in the sand? Okay? Because you're right, in a way. Okay. So, I'm walking, and I'm pushing off this foot. So when I push, what am I doing? What am I applying the force to? Ground. Okay. So, when I walk, I go forwards. So where did I apply the force?
Front foot.
Back. Okay, let me go back a little bit. So, if I apply force down, I go up, right? You push down, you go up. So, if I'm not going up, where am I pushing?
Down.
Down and backwards, right? I'm pushing down, but I'm also pushing backwards. Okay. Something pushes back. What's pushing back? If I'm pushing down, why aren't I sinking through the floor? Right? How full is your cup? If I push down, where did the straw go?
To the bottom.
Down. But I don't go down. Am I going down in the floor? Because the floor's there. What's the floor doing? Pushing back. Right? So I push down and back. The floor pushes up and forwards. And therefore I go forwards. Right? So when you're on the beach, the force of the beach can't apply as much force as the floor can. So we get a footprint because this arrow here and this arrow here can't apply quite the equivalent of the force I'm applying. So I sink, don't get a footprint on the carpet, but I get a footprint in the sand. Because the force up and forwards is a little bit less than the force down and back, and so I sink in the sand. Make sense? Sure? Right? When we talk about opposition, when we're looking at development of running or throwing, but particularly when we're looking at running, jumping type skills and we want this arm swing, right? Part of the arm swing, when we see stage 3 of running, right? Part of that arm swing is because my legs are moving. Right? If you stand up and you keep your arms still and you swing your leg as hard as you can, you're going to fall over. Because the way your body balances that force is to have an equal and opposite force. So opposition, often we don't have to do too much work on the opposition. If we teach the individual to apply enough force, the opposition tends to come naturally. So, to make an object move, I'm going to increase the force application for a given time. Can I apply the force harder for a given time? To make an object stop, I have to increase the time, and we can do that by increasing the distance over which a given force is applied. Gives me a chance to absorb the force. So everybody stand up. Alright, don't jump hard, because we don't want anyone to get hurt. Alright, jump and land with your legs straight. Jump and land and bend your legs. Which one's more comfortable? Bending your legs. You don't get that kind of up your spine that reverberates against your skull. Right? Because when you bend your legs, if I keep my legs straight, I'm not increasing the distance over which the force is applied, the force from the floor as I hit the floor. Right? If I bend my legs, I'm increasing time that force can be absorbed, and I don't get the ding as it hits the top of my skull. When I throw a ball, I want to increase force application for as long as possible. The bigger the step, the longer I can apply force to the ball. So a really good pitcher takes a very, very, very long step. If I'm catching a ball, which is going to sting more, that or this? Catching it in one hand, because the surface area that the ball hits is smaller. So the impact, the force that you're trying to stop, because ultimately that's what's happening. Ball's flying through the air, ball has force. If I'm a good catcher, the goal is to stop the ball. The body in motion remains in motion unless I apply a force to it. A ball in motion remains in motion unless I apply a force. So, if I want to lessen the impact, if I want to make the ball hitting me hurt less, I need to increase the surface area. When we looked at beginning catching, what did we see people catching with? Hands, chest and arms, right? So the brain does this automatically. It lessens the impact. Plus, it can't control the fingers very well when you're looking at little children, but with adults, that's not why you see that happen. So, can't see that very well. Let's go back to how we're going to use this information, right? So, picture number 1. Where's her center of gravity? Right? Somewhere in here. How big is her base of support? She's on point, so it's about that. Right? So, does the line of gravity run through or within the base of support? Through. So is she on balance or off balance? On balance. Okay? Throwing. Pitcher. Where's his center of gravity? Probably in here somewhere. Right? How big is his base of support? Just his foot. Does the line of gravity run through or within the base of support? Anyone? The line of, is the line of gravity, so here's his center of gravity, here's his base of support.
Through.
Outside. Right? Here's the line of gravity. So, is he on balance or off balance? Off balance, is that what you want for a thrower? Right? You want him moving forwards. Okay? If he's on balance, where's the ball going? Right? If I'm like this, is that what you want? Where's the ball going to go? Not very far, right? I want him here so that he can apply force in the direction that I want the ball to go. Okay? So remember what we said, sometimes you've got to understand the concept, because if I'm trying to teach the skill, if I'm watching development of a skill, sometimes what we see is mechanical improvement that leads to development of the skill. Right? The brain works out a mechanical adjustment that results in a developmental improvement in the skill. Okay. What about this one? Misty Copeland, first black principal dancer for ABT. Quite an interesting lady. Right? So, her center of gravity is here, ish, somewhere around there. But where's her base of support in this picture? Right, so we've got here all the way to here. Right, so if we bring that line down, we've got a Y base of support here. So is she on balance or off balance? On balance, right? In your own game, in your own sport, in your own activity, think about how can I use this information? What would I use it for teaching? Right. Why do I want a big step? There's a reason I want a big step. Because I want to increase the amount of time that I can apply force over. Why do I want a straight arm? So when I throw, do I throw like this? Okay. If you watch a good thrower at the point of release, their arm is almost straight. Because I want the longest lever possible to apply force to the ball. So there's lots of biomechanical tricks that we can use to help motor skill development if we understand Newton's laws, center of gravity, and stability. Right, so please, as I said, I used the short version. I'm going to get out a little bit early. Right, but please make sure that you click on the videos and you get to see some more examples of this, because otherwise it can be a little tricky understanding it.